Hey everyone, welcome to Brad and Prad. Hope you're doing well. This is our first playlist for DSA with Java, and we'll be starting off with tries. So, for those of you wondering why we're starting off with tries, our DSA with Java, well, it is often overlooked data structure amongst many students, and there's also hardly a few videos and few resources out there that can where you can clearly understand how the try actually works. And once you understand it, you can apply it in a lot of places. So let's jump right into try. So, what is try? Like, where does the word actually even come from? So, it's conveniently picked up from the word retrieval. So, as you can see here, the word try is from retrieval, T-R-E-I-E, pronounced try. So, what are we actually trying to retrieve here? So, it is a data structure that is used for prefix searches, for storing strings in an intelligent way, such that we can easily do prefix search. So, how exactly are these words stored? So, if you guys are aware of linked lists, just how we have our node, and the node has some value, let's just say maybe 5 here, and it also has a pointer to its next node, and it has a pointer to its previous node. If it's a doubly linked list, then it will also have a pointer to its previous node. Now, how tries work is, like, let's just say I have the word apple. Now, this is stored one by one, where each node represents a character. So we'll have a total of 1, 2, 3, 4, 5 nodes, where we have the first node as apple, the second node as P, the third node as P, fourth node as L, and the fifth node as E. So how would this look like? This would look like A followed by P, followed by P, followed by L, followed by E. Now let's say I have another word that comes in and the user inputs maybe A, B, C, D. Now how do you think this is stored? Now, if you see, I already have A here. So I don't need to insert A again. So that's where it's sufficient now. So there's when you compare it to a hash table, generally in a hash table, when you have two occurrences, that is when a hash collision occurs, and you have the uh, you know required mechanism that the hash table use, either placing it in the next one, or it has some hash function that makes it stores in the correct place. Now, when we have ABCD input, then since A already exists here, I will just skip it. And then from here, now if you see in linked lists just have either one or two links. So this will have the link to the next node, and this will have the link to the previous node. So it will have it at most it can have one or two links. But here in the try, each node can have up to 26 links. Yes, 26 links. Why 26 links? Because there are 26 alphabets. So since I already have A inputted here in the try, then I'll simply have another link to B, and then from B I'll have C and then D. So this is how I can efficiently store a list of words and then find the common prefix among them, which is a popular question in try. So if I were to find the common prefix amongst these two, which is basically nothing but A. So if you see, A is a common prefix. We will get into that slowly, but first let's understand how to implement try. Now, some of you might start thinking this also looks similar to another data structure, which is basically tree. So in tree, what do we have? We have a root node, a left, a right child, and it keeps going like that, right? So again, at each level, each node has at most two links, which is left and right. But here, a trie node, not a tree node, but a trie node has up to 26 links. So how exactly does the node class look like when we try to code it in Java? So initially, we have the root, just like a linked list has a head, and a tree also has a root. Similarly, a trie also has a root. Now, in this root node, what we have is we will have an array of pointers. an array of pointers. So this will be an array of 26 where and is 0 indexed. So where the first one represents A and the last one represents Z. Now, what happens since we're coding in Java, this will not actually store pointers, but each element is an object reference to the next node. So if the user were to insert A first, so what actually happens since A represents the 0th index, at the 0th index, I'll get an edge. So again, each edge represents the node. So this is the node A. Now, this has some object reference, let's just say 2. Now, this object reference is stored here in Java. This is how it actually happens inside. So, instead of a pointer, each element of the array stores the object reference to the next node. So, if I were to have another letter, let's just say maybe C, then I'll have the object reference to that node. So, I'm not actually storing a character array here, but it's rather an array of pointers, an array of object IDs. So it will be of class node itself. Now again here we'll have an array of pointers, and now we'll have a flag. We'll have a flag here, we'll have a flag here. Now what does this flag actually represent? This flag symbolizes whether we've reached the end of the word. So let's just say we've stored everything like, apple into our trie. Now, how do I actually search for this word? How do I know that E is the end of the word in apple? So that is why I have a flag, and the flag is always by default set to false. So if I were to add apple into this trie, I'll show you how it works. So at root level, I don't have any character. Like I said, don't forget that each node represents a character. Now at each node, again, so each node represents a character. Now at each node, you have pointers or object references to the next characters. So at root level, it's not representing any character. Now, if I have the word apple, so how is that stored? So I'll first take A and I'll store it like this. And is it the end of the word? No, it's not. Then I'll move my pointer to the next word, which is P. Now, I'll create a new node for P, and I'll make sure that the node from A points to node P. So let's just say P is somewhere over here. And now this will make another link to P. So this is node P. Now again, node P has the array of pointers where this is Z, this is A, and it also has a flag. Now is P the end of the word? No. So our flag will be set to false. Our flag is set to false. Now this is then continued. Again, we have another P. So from here, let's just say this is P. We have another P that's going. This is P. And now this is again an array of pointers. Flag, false. Since it's not the end of the word. And now after P, we have L. So let's say L is somewhere over here. Then L, we have node L. Again, an array of pointers. And flag is false. Flag is false. Now, is L end of the word? No, we still have E left. So the pointer is now over here when we're processing the word. So now I'll insert E. I'll create a new node for E. And I'll make sure A, B, C, D, E, somewhere over here, it points to this. So this is the object reference to this node. This will again have an array of pointers. just like every other node, A, Z, and it'll have a flag. And now here, since we have no other word over here, and we've reached the end of the word, we'll now make our flag as true. Since we've reached the end of the word, we make our flag as true to indicate that we've reached the end of the word. Now, if I were to do the search operation on this trie to search for the word apple, how would this work? So I'll first start from the root. Okay. And now I'm processing this word one by one. So let's write this again. Oops. Yeah, let's write this again. So I have the word apple. Now I'll first process it character by character. So now first we have A. So now in my root, I will check whether my root actually contains the pointer to A. Now how do I figure that out? Now A is represented by the 0th index and Z is represented by the last index. So in Java, how exactly would I do this? So as you guys are aware of ASCII values, each character has an ASCII representation. Just like for lowercase a, we have 97. For Z, we have 122. Now, how do I change these ASCII values of 97 and 122 to 0 and 25? Since it's a 0 indexed array, we'll have it from 0 till 25. Now, how do I change this? It's very simple. So it will be 97 minus 97, which I get 0, and 122 minus 97, which I'll get 25. So this is how I can intelligently use the ASCII values to get the index of where the object array to that character is, or the character node is. Now, I have my pointer here. I'm processing it character by character to search for the word apple, to check whether it exists in the trie or not. So, I'll take A, I'll convert it to its ASCII value, which is 97, subtract it with 97, which is 0, and then I'll check at the 0th index whether any object reference ID exists. Basically, I'm trying to check whether it's null or not, because if you can check here, I don't have any other object ID references. So by default, all of these will be null. All of these will be null. Keep that in mind. So I'll come here and I'll check that it's not null. Okay, there is an object ID reference. So since there is one, please go there. Let's go traverse there. So I'll traverse to the node A. Now once I've traversed to the node A, there's still another character. I mean, I haven't reached the end of the word. So there's still more characters to process. So now I'm at P. I'll check again, change it to its ASCII value, subtract it with 97 and get the index. Once I get it, I'll check. Is there an object reference ID there? Yes, it's not null and there is an object reference ID. So I'll go to that null. I'll traverse to that node and I'll go to P. And then we'll update the pointer to the next character. Now I'll check in this P node, in the first P node, I'll check at that index, is it null? No, it's not null. There is an object ID reference to the node P. So then I will simply traverse to that. I'll traverse to that. And have we reached the end of our word? No, we still have characters left. We are now at L. Now I'll check at this node, at that index, again L minus 97, which I'll get the index. At that index, is it null? No, it's not. I have an object reference ID which is pointing to the node L. So simply I'll traverse there. Have we reached the end of our word here? No, we still have another character, last character to process, which is E. So our pointer now reaches E. So now when our pointer now reaches E, again, I'll do E minus 97. I'll get the index value. I'll go to that index value and I'll check whether it's not null. Yes, it's not null. It has an object ID reference. So I'll go to that node with that object ID reference. I'll traverse to that. And now I've reached the node E. Now here's the interesting part. Now the pointer is here. That means we've traversed the whole the whole word. Now I'll check where I'm standing right now, which is at node E. I'll check whether my Boolean flag, whether it's true or not. If it's true, that means the word exists in the trie. If it doesn't, then the word doesn't exist. So since my flag is true, our word apple is confirmed that it exists in the trie. So if I were to enter the word, APPL, just APPL, that's it. Now what would happen? Again, I'll simply just traverse, just like before, and I'll come to L. I'll reach L. Now once I reach L, there's nothing else to process further. Then I'll check its Boolean flag. I see that it's false. So that means this word does not exist in the trie. And that is when we send a false. We send a false, saying that this doesn't exist in the trie. Now you may have this question where, well, we actually do have APPL in our trie, and why are we outputting false? So initially, what we are trying to do is, when the user inputs a list of words, let's say apple, bus, and orange, and words like that, we want to only store these words. So yeah, this is efficient for finding out the prefixes, but I actually haven't entered APPL. So when I'm searching for this word, I should actually want false. So this is why we are using the Boolean flag. Now, since you've understood this, let's explore another functionality, should I say, of checking whether a word starts with a prefix. So if I have all this stored, I want to check whether any of the words start with APP, which is app. So this is not a search function. This is more like a starts with function. So if you guys are well versed with strings, the strings has a built-in function called starts with and ends with. So this is how we can use a trie data structure to implement the starts with. So we're checking whether if any of our words in the trie starts with APP. Now here, what do we do? We're not actually bothered with the Boolean flag in this case. I'll tell you why and how. So we have APP. We want to check whether any of the words in our trie start with APP. Starts with. This is a starts with, not a search. Just to reiterate. So again, we process the word character by character, and I have an A, so I'll go to that node, and then I'll update this pointer here. So now I'm processing P. Again, I'll check. So yeah, P exists. So now I'll go to P. Now again, I'll go to the next word, P. And then this, again, I'll check. Yes, P exists. It's not null. And I'll traverse to that node. Now, I've traversed. And since I have reached the end of the word, then I'll output true. Now, what if in a case where I say, does any word start with APE or ape? Now, look at how this actually returns false. So, again, processing word by word, I have A. I'll check the index corresponding to A. It is not null. And I'll go to the next one. So I'll check it the index. Now, since you've understood this, let's explore another functionality, should I say, of checking whether a word starts with a prefix. So if I have all this stored, I want to check whether any of the words start with APP, which is app. So this is not a search function. This is more like a starts with function. So if you guys are well versed with the strings has a built-in function called starts with and ends with. So this is how we can use a trie data structure to implement the starts with. So we're checking whether if any of our words in the trie starts with APP. Now here, what do we do? We're not actually bothered with the Boolean flag in this case. I'll tell you why and how. So we have APP. We want to check whether any of the words in our trie start with APP. Starts with. This is a starts with, not a search. Just to reiterate. So again, we process the word character by character, and I have an A, so I'll go to that node, and then I'll update this pointer here. So now I'm processing P. Again, I'll check. So yeah, P exists. So now I'll go to P. Now again, I'll go to the next word, P. And then this, again, I'll check. Yes, P exists. It's not null. And I'll traverse to that node. Now, I've traversed, and since I have reached the end of the word, then I'll output true. Now, what if in a case where I say, does any word start with APE or ape? Now, look at how this actually returns false. So, again, processing word by word, I have A. I'll check the index corresponding to A. It is not null. And I'll go to the next one. So I'll check the index corresponding to A. I'll check that it is not null. So I'll go to that node. And now I'll update my pointer to P. Now once I update my pointer to P, I'll check whether the corresponding index to P exists, whether any object ID reference exists. Yes, it does. So I'll traverse to that node. And now I'll update my pointer to E. Now this is where the magic happens. So in the last case, P existed. So we went to P. And then since we've traversed the whole word, we output true. Now, once we've reached this P, I go to the corresponding index of E. And I check that it is null. It doesn't have any object ID reference because we didn't insert anything. So since this is null, in a condition where any of the object references, or if there exists no pointer, exists no object ID reference to the next node, then I would output false of the starts with. So this is how I can insert words into trie. I can search for words with trie. I can also implement the starts with. Since we have a clear understanding of how trie works, how its insertion, search, and starts with work, we will check a problem that will actually use all of this together in LeetCode. And we'll also be exploring other problems in this playlist. Thank you for watching.